Hi everyone, my name is Tae Isin and my student ID is MAT2304243. Today, I will introduce the concept of the tangent plane, a fundamental idea in the multivariable calculus. The tangent plane was first introduced by Newton and Leibniz in the 17th century during the development of the calculus. Newton proposed using a plane to approximate a surface's local properties, while Leibniz formalized the idea with the concept of infinitesimal changes. In multivariable calculus, the tangent plane extends the idea of a tangent line to higher dimensions. It provides the best linear approximation of a function near a specific point, capturing both its value and rate of change. Geometrically, the tangent plane is like a best flat surface that closely fits a curved graph locally. This concept is essential in physics, engineering, and even machine learning, where we often need to simplify complex surfaces or analyze local behaviors effectively. So this is the definition of the tangent plane. Let S be an open subset of Rn that contains the point x0, and let f be a function defined on S. The graph of f has a tangent plane at x0 if it is differentiable at x0. In this case, the tangent plane is the hyperplane of Rn plus 1 that satisfies this equation. Now we will use the definition of the tangent plane to prove this first-order approximation theorem. This theorem is as follows. Let S be an open subset of Rn that contains the point x0, and let f be a function defined on S. A. If f is continuous at x0, and there is a polynomial mapping G of degree at most 1, which is a first-order approximation of f at the point x0, then f is differentiable at x0. If f is differentiable at x0, then there is a unique polynomial mapping G of degree at most 1, which is a first-order approximation of f at x0. It is given by Gx equals to fx0 plus the Jacobian at point x0 times x minus x0. We will first prove part A. Suppose that G is a polynomial mapping of degree at most 1, which is a first-order approximation of f at the point x0. There exists a m times n matrix A and a vector B in Rm such that Gx equals to Ax plus B. We know that it is a first-order approximation, so we will have this equation. Limit as h approaches 0, fx0 plus h minus gx0 plus h divides by the norm of h equals to 0. Now we replace gx0 plus h by ax0 plus h plus b. Then we will get this equation. This implies that limit as h approaches 0, fx0 plus h minus ax0 plus h minus b equals to 0. As h approaches 0, we will get fx0 equals to ax0 plus b. Then we will have limit as h approaches 0, fx0 plus h minus fx0 minus ah divides by the norm of h equals to 0. Since th equals to ah is a linear transformation, this confirms that the function f is differentiable at x0. Now we will prove part B. Assume that f is differentiable at x0. By definition of differentiability, this means limit as h approaches 0, fx naught plus h minus fx naught minus Jacobian times h divides by the norm of h equals to 0. We now define the mapping Gx as follows. Gx equals to fx naught plus df x naught times x minus x naught. And this Gx function is the tangent plane. And we define h as x minus x naught. This means x equals to x naught plus h. Then we substitute this x equals to x naught plus h into g x naught plus h. We will find g x naught plus h equals to fx naught plus the Jacobian at the point x naught times h. Now the limit in the definition of differentiability will become this equation. Since the above limit equals to 0, it follows that G is a first-order linear approximation of f at x naught. Now we will look at the example of the tangent plane. Define the function f from R2 to R by fxy equals to sine y squared divided by x times the square root of x squared plus y squared if x not equals to 0, and fxy equals to 0 if x equals to 0. We have to show that there is no plane that is tangent to the graph of f at the point 0, 0. Our goal is to show the derivative at the point 0, 0 does not exist. First, we have to compute the partial derivative of f with respect to x and y at the origin. So, we can find that the partial derivative of f with respect to x is equals to the limit as h approaches 0, f0, 0 plus h times 1, 0 minus f0, 0 divided by h. And then we will then find that the limit, the partial derivative of f with respect to x is equals to 0. With the same method, we can find that the partial derivative of f with respect to y also equals to 0. Now we will let h equals to h1, h2, and t is the Jacobian, which is equals to 0, 0. Then we plug in these values into this equation to get limit as h approaches 0, f0, 0 plus h1, h2 minus f0, 0 minus the Jacobian at the point 0, 0 times h1, h2. And then we will find that limit as h approaches 0 sine h2 squared over h1. To prove that this limit does not exist, we need to satisfy this condition. For all v in R exists xk, yk such that limit xk, yk as k approaches infinity equals to 0, 0, and limit fxk, yk as k approaches infinity not equals to v. Now we let gxy equals to sine y2 y squared over x. We have two cases. Case 1 is when v does not equals to 0. We choose h1k equals to 1 over k and h2k equals to 1 over k squared. So limit h1k, h2k as k approaches infinity will be 0, 0. But limit g h1k, h2k when k approaches 0, we will get limit sine 1 over k squared over 1 over k. And we will then get limit sine 1 over k as k approaches infinity. Since sine is a continuous function, so we can move the limit into the sine function, and we will then get sine 0, which is equals to 0. and this does not equals to the vector v. Case 2. When the vector v equals to 0, we choose h1k equals to 1 over k squared and h2k equals to 1 over k. So limit h1k, h2k equals to 0, 0 when k approaches infinity. But when we find limit g h1k, h2k as k approaches infinity, we will find that sine 1, which is not equals to 0, and so not equals to the vector v. Therefore, the limit h1, h2 approaches to 0, sine h2 squared over h1 does not exist. So f is not differentiable at 0, 0, and hence there is no plane that is tangent to the graph of f at the point 0, 0. So that's all for this example. And here's my reference. Thanks for your attention. That's all for my presentation. Thank you.